our second but first in-person Center for Climatic Research, Climate, People, and Environment Program seminar. For those who are unfamiliar with CCR or CPEP, CCR is the Center for Climatic Research at the Nelson Institute, but most of it is located here on the 11th floor. We have a number of researchers and scientists as well as affiliates involved. The Climate, People, Environment Program, which is supported through CCR, is a seminar series that we're glad to have you here for, but also welcome to take nominations of potential other speakers that we might as we start thinking about our spring calendar. We're currently at Tuesdays at 4, but kind of jumps around a little bit from semester to semester. If you don't know who I am, I'm Uncle Desai. I'm the Reed Bryson Professor of Climate, People, and Environment, and as a result, an organizer of this seminar series. We have a great number of talks through the rest of the semester in addition to today's. Please take a look at the website. We have a few talks from our faculty here in Atmospheric and Oceanic Sciences, but also some researchers and visitors coming in from a couple different places, talking about everything from environmental archaeology to lake sediments of Lake Baikal to thermal remote sensing of the land. So there's a really wide variety of talks, and I hope you get a chance to come to some of those as well. But today I'm here and excited to introduce one of our newest faculty additions to the Atmospheric and Oceanic Sciences program at UW-Madison, Hannah Zanowski. Hannah is, as you can tell from her title, is an oceanographer and a climate scientist. She got her bachelor's degree in physics and math from the University of Arizona, and quickly realized that physics and math is fun, but atmospheric science is even funner, and went ahead and got a master's degree in atmospheric oceanic sciences and then a PhD at Princeton in 2016. After that, she completed several postdocs at the University of Washington as well as the University of Colorado, and also with the NOAA PMEL. Since then, she's been working on a number of projects in both Arctic and other ocean questions, and she joined the faculty here in September 2020, so very, very recent. So this is an opportunity, hopefully, for the CCR and CPEP community. Hopefully, this will probably be the first of hopefully many talks to this seminar series through the years from her, and we'll with one of our two additions to our faculty this year, and the other one, Professor Till Wagner, will be speaking next Tuesday. So the title of today's talk is Arctic Ocean Freshwater and CMIP6 Ensembles, Declining Sea Ice, Increasing Ocean Storage and Export. I'll turn it over to you. Thank you.
All right. Did I turn it on? Hear me? People in the back hear me? No?
Oh, I don't know.
Yes? Maybe I should move this up a little bit. Okay.
That's good.
All right. Awesome. So thank you, Anku, for that lovely introduction. When you list all those things, it makes me feel really cool. So originally, I was actually going to talk to you about some of my more recent work that I just submitted, which is a kind of paleoclimate study about the deep Pacific Ocean. But then I realized that teaching is a lot of work. It takes a lot of time. So here we are talking about Arctic freshwater instead. So this is some work I published last spring. And again, I'll be talking to you about that. So the other cool thing about this project is that when I came to interview here, I had just started doing it, and so I had some very preliminary stuff in my interview talk, and so it's actually really cool to be here and to tell you about the final product, which really kind of turned it into a completely different beast, as science usually does. So again, like Andre said, I'll be talking about Arctic Ocean freshwater and CMIP6 models in particular, and this is some work that I completed in my postdoc when I was at the University of Colorado Boulder. So first, I like to set the stage here, and thinking about the Arctic, if you don't know anything about the Arctic, from my very purely physical oceanography perspective, it's really a whole lot of ice and ocean and rivers. And I'm sorry, Min, I know that it's more than that. From ecologically speaking, think about anything that lives in it. It's really an amazing ecosystem itself. But from my blasphemous PO perspective, it's just these things. So the Arctic is really a very frozen place. There's a lot of different types of ice within the Arctic itself. You have sea ice, for example. So this is the summer sea ice cover within the Arctic in the white here. You've got land ice, so things like ice sheets over Greenland in the yellow, as glaciers as well. And then you also have this region over here in these pinker colors, which is the permafrost, so you're sort of frozen ground, if you will. So a lot of really, really cold, frozen things happening up within the Arctic. It also hosts, the Arctic Ocean itself also hosts a really complex and interesting ocean circulation. You have sort of flow of sort of cooler fresh waters, if you will, from the Bering Strait, so from the Pacific Ocean into the Arctic. You have some circulation within the Beaufort Gyre itself, and I won't, that's cyclonic, I think. I don't think about the northern hemisphere very often. My background's in Antarctic modeling, so at any rate, you've got sort of transport within the Arctic as well, and then sort of flow through these various straits out of the Arctic from the Canadian Arctic archipelago, as well as the Fram Strait on the east side of Greenland, flow inward from the North Atlantic currents, so these are warmer, deeper waters that enter the Arctic Ocean. So you've got this sort of really interesting, again, fairly complex circulation that I'm kind of glossing over here. But this is kind of the picture of what the Arctic looks like in its sort of basis form. And so, like I said, we think about the Arctic as this really frigid, frozen place, but unfortunately the rate at which that is becoming untrue is really disturbing. So the Arctic is one of the fastest changing regions on the planet. We've got all sorts of changes that are going on, and I'm going to kind of go through a few of those in the next few little slides, like I said, to kind of set the stage for what I'm going to talk about today. So the sea ice is declining, and so this is a figure of the average monthly Arctic sea ice extent from June 1979 all the way to 2020. That's in the black line here, so we've got extent on the y-axis and time on the x-axis. And then the blue line is just the trend in that extent. Okay, so you can see from this that very, very clearly there's a very strong decline in the Arctic ice extent. So the sea ice is kind of disappearing. At the same time, the Greenland ice sheet is melting. And so this is results from the INVI team from 2020. We published this in Nature. The Greenland ice sheet has lost over 3,900 gigatons of ice to the ocean since 1992. So really, really huge amount of ice. And so it's kind of a complex figure, but you have this sort of vast change in the ice sheet here on this axis, sea level contribution on this axis. And then sort of the lighter blue colors are the changes related to sort of surface mass changes, so melting, and then dynamical changes would be things like actual calving, glacier calving from the ice sheet and other processes. But the thing that you can focus on here is the darker blue, which is that total. And so what you can see is, again, from these sort of early to mid-90s, and then into sort of the later, and into sort of 2020, this really strong loss of mass of ice into the ocean. So you've got sea ice declining, your ice sheets are melting. I'll go over a few of these too. The snow cover extent, so over the land-covered regions of the Arctic, is declining. You can see that kind of from these trends here from Budrick et al. This is just May snow cover extent anomaly in certain parts of the Arctic. Permafrost temperatures have been increasing, so then you're starting to melt your permafrost. And then river discharge has also been increasing. So you're putting more fresh water into the Arctic system. And so again, this is from 1940 to 2020, and these sort of trends are a little bit, not super easy to see, but this is sort of a general trend and something that we're kind of expecting to continue on into the future. So a lot of really major changes within the Arctic. And of course, the ocean itself is changing too. So this is a figure of the linear trend, so in degrees C per year, of sea surface temperatures within the Arctic in August. And so all of these areas where you actually have temperatures, so the dark gray basically means that it's not statistically significant, but anywhere where there's color, this is sort of the summer sea ice extent, anywhere where there's color is basically a statistically significant trend. So you're seeing these really strong surface temperature warming trends basically through most of the Arctic as well. And all of these things then, of course, lead to changes in the circulation itself. So you also have things like, this is just one example of how the circulation's changed. When you change the amount of ice or you reduce the sea ice, this actually leads to increased eddy activity in the Beaufort Gyre, which is again a circulation pattern within this region here. And so that then kind of leads to changes again within the circulation So you've got all these sort of dynamical impacts that are happening. Again, there's a ton of other things that are actually going on here that I'm kind of just broad brushing so that you know that this place is just really, really changing, and very quickly too. So all the things I've shown you so far impact basically how freshwater is sort of cycled in and out of the Arctic, okay? And so freshwater, if you will, is really water that has no salinity. For my purposes, I am going to define it relative to a reference salinity, but we'll get into that later. So you can just kind of think about this water that's relatively fresh, right? So not super salty water. And so again, a lot of those things that I'm talking about, like the melting sea ice or the melting ice sheets, for example, impact the freshwater within the Arctic. And so this schematic over here is just showing you basically how all of the different ways in which freshwater can kind of enter and exit the Arctic Ocean and the Arctic region. So you've got transport of moisture from the atmosphere. You've got exchange between the ocean and the atmosphere, or the sea ice and the atmosphere through precipitation and evaporation. You've got ocean transport in and out of the Arctic Ocean through these various straits. And then you also have the sea ice transport as well. So again, a lot of these kind of entering in and out of the North Atlantic. And then riverine inputs, again, which become really, really important for the Arctic. Like I said, when I started originally my research, I looked at Antarctica a lot. We don't care about rivers down there, but in the Arctic, you definitely do. So again, all of these things can change the Arctic quite a bit, but they also, again, matter in a much more global context, okay? Because the Arctic itself is not isolated from the rest of the world. It might feel like it is or seem like it is because it's pretty darn far away, but it's not, right? So one of the easiest things you can easiest things to pick up on is that Arctic freshwater actually impacts North Atlantic deep water formation, okay? And so you've got these freshwater fluxes, like I said, through the Fram Strait and the Davis Strait here, all the way through the Barents Sea Opening. These kind of directly interact with the North Atlantic. And so when you're kind of transporting freshwater in and out, you can then affect how much North Atlantic deep water is formed because of these regions here. So you've got things like great salinity anomalies, which occur periodically, where you have a bunch of freshwater that's stored in the Beaufort Gyre that is then released and kind of floods out through here and eventually impacts the North Atlantic and then the overturning circulation. And so once you start to impact the overturning circulation, then you're looking at these much larger scale sort of climate impacts. So again, understanding what's happening within the Arctic and just understanding the freshwater itself is actually really important for all of these things. Now, I'm not going to look at like the major climate impacts today. We're just going to kind of focus a little bit on the freshwater itself. So, naturally, because this is important, a lot of people have already looked at it. Many studies have been done trying to understand the freshwater budget of the Arctic, so literally to like understand what are all the sources and sinks of freshwater, where are they going, where are they stored. So Nares et al. Did a really nice study in 2006, where it kind of basically tried to understand this whole Arctic system as defined within these boundaries. So understanding sort of storage within the various components, like land, the atmosphere, and the ocean, and the sea ice as well as sort of how they're transported in between these things, and also in and out of various straits defined by some of these boundaries here. So again, kind of what's fluxing in, what's coming out. Hain et al. Kind of updated this in 2015. You don't need to read the numbers here, don't worry about it. It's just kind of a table showing you that we've thought a little bit about this, kind of thinking about 1980 to 2000 observations versus 2000 to 2010. And then he looked at models to kind of look at sort of the 21st century changes as well. So I tend to find that schematic to be a little bit overwhelming, so I made my own. And this is my really, really simplified version of the Arctic. So I think of the Arctic, it's just the sea ice and the ocean, and there's some riverine inputs, there's some exchange with the atmosphere, and then there's sort of transport in and out of the Arctic Ocean itself through these various passageways. And for my purposes, I'm not even going to do a budget, because that's a huge pain in climate models. And so what I'm going to do instead is just really focus on the sea ice and ocean components of the storage and the transport. So the storage, again, we'll be looking at the storage in the sea ice for the freshwater and then in the Arctic Ocean itself. And then we'll just be looking at our imports and exports. So inputs is going to be the liquid flux through the Bering Strait. And then exports is basically everything else, both liquid and solids, come out of the Arctic. And so we actually also have the Barents Sea input as well. But again, my focus is just on this, so I'm not really going to be looking at a budget. I'm just going to be looking at those particular terms and thinking about what they look like now compared to observations and how they've changed. So let's kind of change gears a little bit here and think about models, right? So I'm going to be using a lot of climate models within this study. And so freshwater in the Arctic has also been studied in models, and there's been a lot of studies that have looked at freshwater storage and transport in the Arctic. So I'm very quickly going to go over a couple of things here. We're just looking at the Coupled Model Intercomparison Project. So we did big CMIP studies. So we have CMIP3 and then CMIP5. So these are sort of the trends in CMIP3. This is from Holland et al. 2007. What we're showing is the model liquid transport change from mid-21st century minus mid-20th century. This is just ocean freshwater transport in the Fram Strait, the Barents Sea, and the Bering Strait. And then over here we have the solid and liquid freshwater storage. This is the 1990 to 1999 mean. And so this dashed line here is the observations, and then the actual individual bars in all these cases are actually the kind of the models that were part of this study. And so if you look at this, you kind of pretty clearly see that, well, the models didn't agree, right? You've got different signs of changes in terms of what the freshwater looks like. And what will happen in terms of what will happen in the future. Same kind of goes for the liquid and the solid freshwater storage, where for the most part you've got the same sign of storage, but again, pretty broad disagreement among the models about what their mean states basically look like and how things are going to change. So that's kind of the name of the game with the CMIPs. Models tend to disagree with each other. And in this particular set of models, not all of them had these small straits open in the Canadian Arctic archipelago. And that's actually really important because it means that all of your freshwater has to come out through the Fram Strait instead. And so this is kind of a big deal here. But fast forward a little bit to CMIP5. And so now most of the models have these tiny straits in the Canadian Arctic archipelago open. And then this has to do with model resolution itself, why you can't have these things open or closed. So this is freshwater content trends in CMIP5. So now this is the multimodal mean projected freshening trend from 1951 to 2100. So we're saying, okay, go from 1950 all the way to the end of the 21st century to see how we might expect things to change. And so these are these sort of different representative concentration pathways, or these different sort of future emission scenarios, going from sort of low emissions to really, really high sort of emissions. And what you see overall is that in the multimodal mean, you're kind of tending to get this sort of increase in freshening, especially within the Beaufort gyre region. Now, one thing I think to keep in mind is when you're looking at a multimodal mean, it really hides a lot of differences across models because it's an average, right? So, as an example, this is single model liquid freshwater content. This is the change in freshwater content from the end of the 21st century to the beginning, and just one of those RCPs. Okay, and this is just an example of two of the models that were in CMIP5. And what you can see basically is that the areas where the freshwater content increases over time or where it's changed is really, really different. So you have these really different spatial patterns where in GFDL, you've got strong freshening in the Beaufort gyre region, whereas in the MPI model, it's kind of more located in the central Arctic. And again, you're averaging over all of these to kind of create a picture like this. So I'm not saying that's wrong, because we all have to do it, especially when we're trying to show things about CMIP6 models or CMIP models in any sort of like reasonable way. It's a huge amount of information to kind of condense and show, but it's just always something to keep in mind. So in this study, Xu et al. Actually also looked at Arctic freshwater flux changes, so kind of looking at some of these various straits, like I said, and these are freshwater flux anomalies here, and kind of looking at solid and liquid transport. And the idea is that in some of these cases, you see sort of increases in the freshwater transport or freshening of the Arctic, kind of declines elsewhere. So that kind of leaves me finally to my research question, which is trying to understand what the state of Arctic freshwater storage and fluxes are in CMIP6 models, and try to understand how that's going to change in the future. So like I said, this is a published paper. If you're interested in, that's a citation. Well, we can talk more about it afterward. And so again, my goal here is to characterize the CMIP6 model Arctic freshwater storage and export during the end of the 20th and the 21st centuries. And so to do that, I'm going to compare all the models from CMIP6 that have at least 10 ensemble members for their historical simulation. And this is because I actually want to understand something about the spread and that variability. We're not going to talk a ton about internal variability here, but it is something I think that's important in the terms of our results. Typically, they'll have fewer for these future forcing scenarios. Other major things that they actually provided me all the variables I needed to compute the fluxes. You'd be surprised at how quickly that gets rid of a lot of models. And so out of I don't know, there's more than 50 models in CMIP6. Out of that, they left me with 7 at the time. And thankfully left me with 7 at the time because it is a beast. And all of these models have nominally 1 degree ocean sea ice resolution. So not super high res in this case. We'll be looking at 2 different sets of simulations in CMIP6. So the historical simulation, so historical forcing. We'll typically looking at 1980 to 2000 averages for comparison to observations. And then we'll be looking at the shared socioeconomic pathways. So these are now the sort of future forcing scenarios for CMIP6. Okay, so they went from being called RCPs to SSPs. Some things changed in between. The only thing you really need to know is that I used 2 different simulations, this 2.6 and this SSP5-8.5. And these numbers here at the end define the sort of top of the atmosphere radius for forcing anomaly at the end of the 21st century. So global warming, 8.5 is your let's burn the world to the ground, because that's what we like to do. And we'll typically be looking at the end of the 21st century, so 2080 to 2100 averages. So how do we define things? So freshwater storage is just the volume in the Arctic, so you literally calculate the volume of the freshwater within the Arctic. And so freshwater, when we think about it, is just how fresh the ocean is relative to a reference salinity. And so we're using this reference salinity of 34.8. That's traditionally what the average salinity of the Arctic Ocean is. So that's why we're using that. And so anything that's sort of fresher than that will count as fresh water, and anything that's not will not. So again, you're integrating this over the whole volume of the Arctic Ocean within these boundaries of these straits here. And then the depth you integrate over it down to this reference salinity isohaline within the Arctic Ocean. Transport is very similar. You still have this sort of reference salinity where you're either transporting fresh water or you're not. Multiplied by a velocity through an area perpendicular to that flow, so through these different boundaries here. And in this case, we'll do the 4, and then we'll do the Barrow and the Nares Strait as well, because those are liquid. All right, 30 minutes in, we finally make it to results, so yay. Okay, so let's kind of set things up here. So this is model ensemble means sea ice thickness, and then I'm going to show you freshwater column. So sea ice thickness is actually kind of directly related to storage, as we're going to see. And so this is the 1980 to 2000 average sea ice thickness, so in the blue colors here. And on all of these little contours are ice concentration contours. Okay, they're always the 15% sea ice concentration contour. The yellow is for the historical simulation. The middle orange color is for SSP1-2.6, and then the darker red color is for SSP5-8.5. So I'm kind of giving you an idea of where the ice is going as time changes. So we have historical thickness covered with the sea ice coverage change, basically. So if you look at thickness, you can see that in some models you have really, really thick Arctic ice that's like more than 5 years. I think the average thickness is 2 to 3. Don't quote me on that. Steve's in here, he knows. And then you have other models that have considerably less thick ice in that region. And then as times change, in this SSP5-8.5 scenario, by the end of the 21st century, in some of these you have these contours here, like in UKESM, in IPSL, and then also CAN-ESM, where in this 20-year average, you actually have an annual average, you have completely ice-free Arctic, basically, by the end of the 21st century, in this burn-it-to-the-ground scenario. Less so in all these other models, and also in different scenarios. So a lot of changes, a lot of difference among the models, and that's going to be the name of the game in this as well. We can look at freshwater column 2. So freshwater column is basically just the thickness of the freshwater layer in any given point within the Arctic Ocean. All right? And so this is now has units as meters. So we've got our 7 models, and then we have PHC 3.0, which is sort of observations in comparison. So again, if you look across these, you can see some that stick out like a sore thumb, where they have Arctic mean states that are way, way, way too fresh. And so as a result, you have a really, really thick freshwater column, right? And then in some models like CNRM, they actually kind of do pretty well in comparison to PHC3. So these things then, of course, impact the freshwater storage itself. And so we've got solid storage here, and we have liquid storage here. And so this is in cubic kilometers versus all of our 7 models here. This sort of magenta or pink dashed line is observations from Hain et al. 2015. And then these, again, are box and whisker plots, so they're actually showing the spread of the ensemble members for each of these simulations. So some of them are getting kind of close to obs, probably by chance. And you can see, for example, in the freshwater, so in the liquid storage here, and do note that the axes are like an order of magnitude different for solid versus liquid. I mean, the Arctic Ocean's big. So like we saw in CAN-ESM, because it has this really, really thick freshwater column, its freshwater storage is unusually high, right? So it's much, much higher than any of the models. And then, like we saw in UKESM, which have really, really thick ice, you see sort of really, really high freshwater storage within its solid component. So again, kind of major differences among models. There's a couple of other things you may want to think about in terms of these spreads. They have different numbers of ensemble members, and also the volume in the Arctic is not always the same across the models. This is really annoying, but it happens. But it only leads to something like a 10% error in differences. So some of it's related to volume, but most of it is just that the models' moon states are different. So we can then kind of think about what happens then in the future. And so now what I'm showing you are future solid and liquid freshwater storage changes. So our models are always going to be on the x-axis here, storage on the y, and then historical simulation, so that's 1980-2000 average, is always going to be in gray. SSP1-2.6 is going to be in this blue color, and then 5-8.5 is in the yellow. So that's your kind of map. They're always going to follow that, for most of this talk. So I don't change it up on you. And the error bars here are just plus or minus 1 standard deviation of those ensemble numbers that we have. So you can see the freshwater storage definitely tends to decline, and this is because your ice is going away. It's sort of a stronger decline for 5-8.5 than 1-2.6, like we'd expect. And then the liquid freshwater storage is increasing, partly as a result of this, but also for some things I'm not showing you, like increases in river discharge, as well as increases in P minus E, so precipitation minus evaporation. So overall, you kind of see this trend. But if you want to go to understand how you go from that 1980 to 2000 to 2080 to 2100 average, you kind of want to look at time series. So now we are going to take the multimodal mean for this. So I have 7 models, remember. And how I deal with this, because they have different numbers of ensemble members, is I take the mean of all those ensemble members from each of the 7 models. And then I take the mean of that to get this. So I actually have a mean of 7 things that, just aren't, completely weighted too much by the number of ensemble members. And the envelopes are not your typical 95% confidence interval. They're just the max or the minimum value of any of those 7 ensemble means for each. Okay? And that's to give me a really sort of stringent understanding of like how different these scenarios are by the end of the 21st century. So again, nothing too special here. They show largely what happens in between, going from gray to blue or yellow. But again, largely declines in sea ice. Everything's kind of going towards 0. There are some differences between the 2 scenarios by the end of the 21st century. And then sort of increases in liquid storage that tend to be larger for SSP5-8.5 than SSP1-2.6. So again, in this case, you have these really, really big envelopes here because CAN-ESM, that model with really fresh water, is just making everything really huge. So that's kind of disguised within that. We can move on to fluxes then. And so again, we're going to kind of go back here and we're going to look at our box and whisker plots again. These are solid spreads of the solid fluxes through all of those straits. Our sign convention is a positive flux into the Arctic, a negative flux out of the Arctic. Dashed line are observations from Hain et al., and then these sort of gray bars are plus or minus the error in those observations, if they have them. So a lot of disagreement among the models again. Sometimes they don't even disagree about the sign of the changes. Sometimes they fall on both sides of the observations. There tend to be some biases, a lot of stuff going on under the hood here. So a lot of disagreement, even within these 7 models themselves. So still quite a bit of work to get done. We can now look at the future. So again, these bar graphs are going to set up in the same way. Do note that the y-axis scales are really different. So in terms of ice fluxes, Fram Strait does most of the work in the Arctic of fluxing solid the solid freshwater out. And you can see you've got these major declines even in these future forces scenarios. And again, this is largely because, again, your sea ice is going away. If you melt your ice, there's nothing to flux out. And this tends to be the case across the models. If you want to understand how we got there, this is sort of the time series of all of those in the multimodal beam. Again, nothing particularly exciting here except that the ice is going away. And so in some of these simulations, you might start to see some difference between the SSPs and the future force scenarios. And this only tends to be the case in regions where you actually have large ice fluxes to begin with. Otherwise, it's just too easy to melt it all away, and it doesn't matter because everything's zero. We can look at historical liquid freshwater fluxes as well. These tend to vary like the ice, so kind of different across models. There are some better agreement. It tends to be we have a little bit better agreement in the liquid fluxes compared to the solid fluxes across models, but it's not like super great. There is one model like IPSL, for example, that tends to actually get at least one or a couple of ensemble members that actually hit the observations for most of these straits, which is surprising, but again, it's partly because this model has the highest number of ensemble members. So again, these kind of comparisons, you've got interesting biases all over the place, kind of big spreads. But again, not always huge agreement within this. So we then look at the future. Again, these axes are not all the same, so just kind of keep that in mind. There's some interesting behavior going on here. So for the most part, what you see is increases in freshwater fluxes out of the Arctic. So in the Barrow Strait, the Nares Strait, especially in the Fram Strait, sort of major increases in the fluxes there, and then in Davis as well. Some more interesting behavior is in the Bering Strait. You've got models that sometimes they show an increase, sometimes they say a decrease. They're a little bit more stable than some of these other regions, and I'll talk about that, why that's the case in a little bit. And then same in the Barents Sea. You see that everything kind of changes sign, right? So this is a really interesting area where you were fluxing freshwater into the Arctic, and then now into the future, you're actually going to be an exporter of that. So it's, sorry, you were taking one freshwater out, and then now you're going to be an importer of freshwater. Get my signs right here. So, we kind of want to understand why that happens, and I will get to that in a second. Again, kind of thinking about how things change over time, there are some interesting behaviors here if you stare at this for long enough. Bering in the multimodal mean is relatively stable in comparison to some of these other straits. Some of them you kind of see this interesting thing where you increase the transport out of the Arctic, and then it kind of declines toward the end of the 21st century. Sort of the opposite of Davis. A lot of curious things happening here. And then in the Barents Sea, you sort of see this kind of increase in that transport that you just saw. So to understand that, and particularly understanding why the Barents Sea Opening liquid flux changes some in the future, if you go back to understanding our transport equation here, if you look at this, again, this is our volume fluxes in and out of the Arctic. There are two different ways in which you can get a sign change, right? So you can have this be positive or negative, or you can have U be positive or negative, okay? And so we want to understand then, if we want to understand what's driving the freshwater changes, we either want to know if it's a volume change, so something to do with the velocity itself, or is it a salinity change, right? So we want to know which of these components matter. So we'll decompose our freshwater fluxes to get our separate time-varying salinity and volume contributions. So this is our little thing. I'm only going to be talking about sort of the U bar S prime, so the contributions from the salinity anomalies, or the S bar U prime, which is the contribution from the volume anomalies. Okay? And so we're not going to be kind of thinking about S prime, U prime, or any of that. And all of our anomalies are going to be relative to this 2000 to 2100. So we can go back to our liquid freshwater fluxes here. So you've got all these kind of changes here. And then now what I have is this decomposition. So purple colors, or the darker colors tend to be SSP1-2.6. Purple is for volume anomalies. Green is for salinity anomalies. And then the lighter colors are for SSP5-8.5. So when you look at Bering Strait, basically what you see is that you have a somewhat decline in the volume, but it's compensated by a freshening of the water that's entering in that region. And so that's why overall the multimodal beam is relatively stable, all right? So you've got two competing factors and they kind of cancel each other out. In Fram Strait, they kind of both act in the same way always, so they kind of lead to this picture that you have here. And in the Barents Sea, nothing's really happening with the volume, so there's not a transport change. It's actually just a salinity change that's happening within this region. So it's a freshening of those waters that then leads to this change in sign within the Barents Sea. So the last thing I'll talk a little bit about is just kind of thinking about this multimodal beam. Our multimodal beam really hides major model differences, particularly in the straits west of Greenland. So this is just the volume fluxes. This is not freshwater flux anymore. This is just thinking about transport. Okay, so you've got all your different models. So you've got Nares Strait, Barrow Strait, and Davis Strait. You've got your two different simulations here, going from the historical period. And if you kind of stare at these long enough, you start to realize that like we're averaging over things that have different signs and trends. You've got, kind of things where you, for some of these models, they actually like reverse the sign of the transport itself, and then it kind of recovers. A lot of really crazy stuff is going on within these regions. So the Canadian Arctic archipelago is still an area that we don't really do well, and that's not surprising. It's difficult. And we have the scales of resolution that we actually need there are much smaller than we can resolve in a typical one-to-one model. And so, these are, again, we have these sort of averages and kind of an average understanding of how things change, but the individual models tend to tell a really different story, and this is kind of always the name of the game, right? There's this battle between showing a mean and saying they do this, but even within these 7 models that I'm showing you, again, they are all telling you a very different story about what will happen at the end of the 21st century. So I'll kind of leave it there. The things we kind of found were that freshwater storage and fluxes over 1980 2000 really vary widely across the models, and few are consistent and close to observations. So that's still the case, that's been the case. Having models that get the mean state right and the variability right is just really hard. This is not meant to like get mean to our modelers, because having a climate model that does everything right is, that's what we're all, that's our unicorn, right? So this is not meant to be like, oh, well, you need to do the models better. Well, that's really easy to say. It's a lot harder to do. And so in the future, all our models exhibit these really strong declines in solid storage. And again, that's because we do expect the sea ice to continue to disappear. And also kind of changes in the fluxes, really as the sea ice coverage declines. The liquid freshwater storage, they generally increase out of most of these straits in the future, but it is a bit of a mixed bag. And so these are some of our exceptions, like the Barents Sea, where we expect the salinity changes to kind of dominate everything. And then the Bering Strait, which is in the multimodal mean is fairly stable, but not within individual models. And so the magnitude of these changes, of course, are all highly model dependent. It depends a little bit on, again, those ensemble members as well. And all of them do, though, suggest an acceleration of this Arctic freshwater cycle and basically a dynamically different Arctic by the end of the 21st century. So I will leave it there, and if you have any questions, feel free.
So we can see the audience here. Questions? And encourage students if they could take first dibs on a question if they got one.
Yeah, so one of your conclusions is that the models vary a lot with the storage and flux terms. And you can't tell for the future, but for at least those historical models, do any of them do better or worse to actual observations? Like, are there some models that are doing a better job versus a worse job? Did you look into that?
Yeah, I mean, I actually have a figure somewhere that's like a summary figure in the paper where it kind of looks at those and like a grid. It kind of says these are the ones that kind of do fairly well in the historical period. Based on these, I mean, we can go back and kind of just eyeball this. Let's like look at this, for example, like, okay, we can say that MyRock is doing okay on MyRock 6 is doing okay on the solid storage pools, getting close to that region. In the paper itself, we actually kind of created some error bars here to kind of help with that. It's a pain to explain, so I left it out at the top. So some of them do okay. Like I said, IPSL seems to do really well with those liquid fluxes. And we talk a little bit about the ones that do that. So they're not, most of them aren't complete, like even if their storage seems to be quite different, they're not so horrendous at that. They tend to do, I think, the worst in the solid flux region, and that's because, again, doing ice is hard. You've got all these little like places and things, and they're too thick in some places, not enough. There's a lot of biases. So I think the better your mean state is, the better you're gonna be able to get this, but then you also need to think about the variability. So it's a little bit of everything.
Yeah. And then a related question would be, how good is our understanding of solid freshwater storage in the Arctic?
Well, that is a great question. We really have struggled, I think up until like ICESat-2, which was recent, to measure ice thickness. And so a lot of it, in terms of the observations for this, I know we talked a little bit about this last week in group meeting, the observations for this are based on an average thickness. So Haynes just said, let's just assume it's 2 meters thick everywhere, because they just didn't have things from 1980 to 2000. Or you can use like biomass, which is like an reanalysis interpolated like hot mess that we don't use. And there are, a couple of things that, but that's the best we can do, right? Like if you don't have the thickness, you can kind of guess from freeboard and other things, and this is getting into satellite territory that I don't understand. So we, especially with the ice, I think it's still really a struggle, but hopefully now if we can actually measure thickness, that will go a long way to improving that. So we're going there, and our ice modelers and our ice observationists have been thinking about this for a long time. So
I have 2 questions.
All right.
First one is more general. How does the change in freshwater in the Arctic change the AMOC?
So if you basically flood the North Atlantic with a bunch of fresh water, you stop forming North Atlantic deep water, because you actually need things to get salty and dense to sink. And so if you don't have that, because you freshened everything, you made everything lighter, you kind of shut that off. Or to make it decline, let's be careful about that. I see you, Liz. I know we don't shut off AMOC, that's, we've talked about those things here. So yeah, you can definitely change it just by changing the salinity of that region, because it's really largely salinity controlled. So.
And the second question would be, you can pull out of the AMOC from the model. And does that agree with what you see with the change in freshwater?
I did not look at AMOC. I think there's been some studies that definitely show it declining. I do not know if they connected it to exactly to only freshwater change in the Arctic, because there are other dynamical change things going on. But I do know that in a lot of the models in CMIP6, you see this decline in the AMOC, and in some cases it's pretty wild.
So if you have, for UK model, would that mean the AMOC is just shut down or not?
I don't know. That's a really good question. If you got rid of all the ice, because it's so thick, but my guess is that you have more water. It would depend on if you actually transport it out of the Arctic, though. So maybe it all sits in the Beaufort Gyre, maybe it doesn't. But that's a really great question. I don't know. So. Yeah,
are there any seasonal variations you observe when you are talking about Arctic freshwater budgets and excluding the atmospheric components?
I did not look at seasonal variations, but I am sure there are, because, summertime when there's not a lot of ice versus winter when there is, and kind of the times in which you can actually transport ice through, especially through some of these passageways in the Canadian Arctic archipelago, like in Nares in winter, it actually gets completely blocked off. So your ice transport goes to 0 because everything's frozen. That's changing too now. So there are definitely seasonal variations, but it is not something that I looked at.
So there can be a possibility that some of the models are not able to resolve the seasonal. So it might be a case that for a particular season, every model is performing good, but if we want to know about the biases, if we start isolating the seasons, we can get some insights.
Yeah, I think the seasonality would definitely play in kind of annual averages and then these sort of decadal averages. So I didn't do that, but that would definitely be important, right? Because they may be biased more in one season versus the other. That's, again, not something I looked into, but I would expect that to be the case.
Steve?
Well, Hannah, following up on Rudra's point about variability, seasonal variability, what about the point you made early in the talk about these great salinity anomalies where you have freshwater buildup in the Beaufort Gyre and it looks like we may be ready for another one soon? Do the models simulate that well at all, that kind of short-term decadal variability?
I'm honestly not sure. It's not something that I looked into. I know that there are modeling studies that have thought about the Beaufort Gyre freshwater lease, but I don't know about what time scales or any of that they do it. And not in the kind of coupled realm. I don't know who's looked at that, unfortunately. But I would not be surprised if somebody has.
Well, given your results for the problem simulating the time mean, I'm guessing they probably don't do a great job.
Yeah, that would be my guess.
Variability.
Yeah.
Do you think that all this range of variability in the models is because of the physical parameterizations of eddies you're not resolving in the ocean, or is it because of ocean and cryosphere and coupling?
It is probably all of those. I know that ocean, if you improve the ocean resolution, the ocean and sea ice resolution, that can get rid of some of your biases, but it does not get rid of all of them. So I do also think it is a coupled problem as well, which is always the struggle. And again, also some of it has to do, again, with a lot of the transport in and out. So you can really, really mess up your Arctic mean salinity, for example, by what you're transporting in the North Atlantic. And there, again, are all these sort of compounding factors. So unfortunately, it's a yes, it's all of those. And I'm not sure which one matters the most.
It seems like there was really dramatic changes in the sea ice.
Yeah.
Big removal.
Yeah.
Do you have access to, for example, cloud fields and things to see whether those have very different cloud fields as well?
Yeah, technically, yes. If we go into the models and look at the atmosphere, I'm sure we can look at that. So, and I'm sure that matters.
Very cool. I'm going to ask maybe a more naive question. I don't think about ocean models very much, but I do think about land models a lot. And at least in that world, for a lot of systems, the rates of storage and the rates of transport or fluxes are often correlated. All right. And I was just kind of curious to what extent that would, like, are there any kind of relationships here among models that have higher storage, have higher transport, or vice versa, or higher solid transport, have lower liquid transport? Or I'm just trying to think about ways to like diagnose or benchmark these models under kind of different ways like that. I don't know if that's possible.
No, I didn't particularly look at it. I suppose I could just sit down and think about it.
Yeah.
I didn't look at it for this paper, but I kind of wonder that too. Though, does it, how does this impact it? And my guess is that there maybe won't be as clear of a relationship because it will kind of depend on how things change within each of the models as well in terms of that. So, but I always thought it was curious that this stupid S structure, for lack of a better word here, they kind of look very, very similar. And it's something that's bugged me, and I don't actually know why it is, and I don't know if it's related to something about which model it matters actually, which sort of subsystem, if it's a coupling, that they kind of all follow that pattern with the exception of UKASM doing its own thing up there. But I wouldn't kind of be surprised if some of these things were then related. I mean, I guess UKASM theoretically could flux more ice out of the Arctic because it has more to begin with. But, and maybe that's kind of the easiest thing to kind of guess. Yes.
Very cool. Thanks.
Yeah. Awesome.
Again, Liz in the back.
Starting around 2012, there was a lot of fresh water that came out of the Labrador Sea. Now the subpolar region is a lot fresher. I believe that it came out of the Labrador Sea. Kind of sounds like some of the stuff that you're discussing. This is happening today. How much of an internal variability component do you think there is versus is this, sea ice melting because of greenhouse gases, a force component? Any wild hypotheses?
Alex wrote a paper on this. I can't remember the results. She actually looked at the time of emergence, right, from some of these fluxes, and I can't remember which ones have emerged already. But I just kind of looked at like which one of these, and this was only based on the CSM large ensemble and that sort of stuff. I wish I could remember, but I don't have any wild guesses. I'm really curious about that too. So.
Right. Well, looks like we're exhausted.
Questions out,
Questions
yeah.
maybe exhausted you, but thank you.
All right, thank you guys.
It's a wonderful talk, and if you're, we'll be continuing some Arctic and polar themed talks with next week with Professor Till Wagner, who's going to continue talking about some sea ice work. So stick around as we kind of continue this polar cluster theme as well through many of our talks. So let's give another hand to